ice-free West Antarctica. So we're going beyond the tipping point.
Good morning. Thank you for having the possibility to be here today. I'm Johanne Klages, but as you see, representing a large group of people. And so we set out with our icebreaker Polarstern in early 2017 to understand more the behavior of the West Antarctic ice sheet during warmer than present past periods. And one of them, we were quite lucky, is the transition from from the greenhouse climate across the coolhouse climate into the current icehouse climate. So if you look at that, just for orientation, so we have the large East Antarctic component here, West Antarctica here. So this is where we drilled the site with the MEBO seafloor drill rig that you see here. Some of you might remember a paper that we published a couple of years ago on this with material from the same expedition. So we drilled into mid-Cretaceous strata here on the transition from the inner to mid-shelf part of the Amundsen Sea embayment along the Pine Island Trough. And when we go further seawards, then we come here to another site that we drilled maybe 50, 60 kilometers further seaward here. And as you can see, so we drilled through Oligocene strata into latest Eocene there. And so if you look at that record here, then we wanted to understand, of course, how much and if at all grounded ice already covered West Antarctica at the time. You see a 10-meter record here, extremely fine-grained material here, so silty clayey silt overall. But if we first look at the age constraints we have, so we have a couple of strontium isotope ages combined with paleomagnetic information. Luckily, in those 10 meters of core, we see a reversal right here. So together with the strontium ages, we could constrain this reversal to the transition from the Crone C13R to C13N, which interestingly coincides with the early Oligocene isotope step. So somewhere on the planet at that time, a lot of ice was probably formed, but so far we don't really understand where that was. So, but looking at this record here, so first of all, we drilled into a key period of initial Antarctic ice sheet formation. As I said, the early Oligocene isotope step, but we don't see any indication for the presence of nearby grounded or rafted ice. So as I said, extremely fine-grained, no sand or gravel whatsoever. But at the same time, we see strong evidence for dense notophagous forest vegetation similar to southern Patagonia today, and active surface runoff of rivers and creeks. We had surface air and sea surface temperatures that you can see here that match well and indicate mean summer temperatures of around 11 degrees Celsius with a mean precipitation of around 1,000 millimeters per year. So overall, we reconstructed a cool, temperate environment here, and together, bringing all that together that you see here, so biomarker information, forum assemblage information, grain shapes that you see here are not angular at all, but more sub-rounded to well-rounded. So the grain shapes also further suggest active surface runoff altogether, for example, and most likely by rivers and creeks. But we see a marine environment. So we have forams in there, we have Bulboforma in there. It was a shallow marine environment, probably 50 to 200 meters, so a mid-outer shelf environment, but already a marine environment. And that, of course, is an important finding, because with that record we now know that this part of West Antarctica must have already been below sea level. So with that, we can only, for that area, so for West Antarctica here, we can only validate the minimum topography published by Paxman et al. In 2019, and basically reject the medium and maximum topography suggested in that publication. We see here data evidence for the same time frame, so the EOT basically, around the continent that is so far available. At the same time, we also see examples for different ice sheet simulations for that time period. I chose those because they're really contrasting here. So we see one simulation by Wilson et al. 2013, basically suggesting a full glacial condition here with an LGM-like configuration of the ice sheet. But at the same time, we also see simulations by de Conto et al. In 2007 that rather suggest a minor size of the Antarctic ice stream at the time. So, but we also see available terrestrial and marine temperature record, but also ice sheet extent reconstructions here in Pritz Bay, here in the Ross Sea. And, but we also see a large data gap that is still present for West Antarctica, most important for us to understand how the West Antarctic ice sheet reacted during this fundamental climate change crossing from greenhouse climate into the current icehouse climate. But you can also see here that the warmest ocean temperatures were here offshore Wilkes Land, northern Victoria Land, rather cooler climate here in the other regions, but now with the new record we can fill this West Antarctic gap pretty nicely with, as I said, air temperatures, sea surface temperatures, also information about ice sheet presence. And with all that together now, which possibility do we have now to improve our understanding of Antarctic ice sheet extent during this past fundamental climate change? And to do that, we took all that information and I approached our paleoclimate modelers to try bringing together our RV Earth system model that you can see here, the RV Earth system model 2.1, which incorporates an atmosphere component, an ocean component, and interestingly also a landmass component with interactive vegetation. And that Earth system model we then asymmetrically or asynchronously coupled with the parallel ice sheet model. So if you look at that and start with the topography here, and with the evidence for West Antarctic topography at the time, taking our new record here and the record published by Köhnen et al. In 2020, then we can basically reject, as I said, those two scenarios here and focus on the minimum topography. With that, we forced the RV Earth system model with the 34 million year pre-ice climate. Took that information and focused on this year on the 840 ppm scenario, which corresponds best to the Pagani et al. Data for the same time frame, so 3 times pi CO2. And then look at the ice sheet extent with the PISM model, then taking that again and going back and checking the climate at the time, so for the air temperatures, but also for sea surface temperatures, and compare that to the available data that I just introduced. Then we can also, as assumed already, focus more on the 3 times pi CO2 because those are the records that best match the simulated temperatures here. Then can also reject here the 1 times and 2 times pi CO2 simulations here and focus on that result. But then checking now with our new record from West Antarctica, this confirms our data so that we don't have any indication for grounded or rafting ice in West Antarctica here, but see ice presence here in the Ross Sea already and also in Pritz Bay, which corresponds to data evidence from Galliotti et al. Here and also from numerous publications here for the Ross Sea, for example, Pasquier et al. And then from there, we did a couple, and you can see that here, we coupled back and forth because so far we don't fully coupled dipism into the RVESM. So what we did was asynchronic coupling every 3 climate years and every 300 ice years, and did that a couple of hundred times back and forth. And this is basically now what you see here. So this is the ice sheet cover result for the early Oligocene glacial maximum. So the time following these early Oligocene isotope step. As I said, that matches nicely with current data that we have available. So we have ice presence here and there on these 2 sites, but we don't see any indication at the drill site that we acquired in early 2017 here. So that matches quite well. For air temperatures, this is the simulation. If we compare that to the available data sets at the time, we have also a quite nice correspondence in between data and simulation. If we focus on sea surface temperatures, it's a similar image that you see. Warmest temperatures here in the Wilkesland sector, and also maybe down to Pritz Bay here in between Australia and Antarctica. So warmest temperatures approaching the continent here. And that also probably initiating this early ice sheet, so the ice sheet nucleus at the time. And then we also check for vegetation, which also very nicely corresponds to our data evidence for evergreen and deciduous trees and shrubs. And so we have 90% nothofagus forests there, but also some conifers, which matches very nicely. So what did we get? We showed the ice sheet coverage was highly asymmetric between East and West Antarctica, at least a 7 million year lag in between the glaciation of East and West Antarctica, so West Antarctica much later. West Antarctica was still covered by cool temperate nothofagus forests, and we see with that new information that there's a high significance of differential regional Antarctic ice sheet response for fundamental past, but probably also future ice sheet change. Thank you.
Thanks, Johanne. We don't have time for questions,
Okay.
I'm afraid. But please find Johanne at the break.